This is the Amp Hour Podcast, recorded January 4th, 2017, episode 330, an interview with Zach Fredin. Welcome to the Amp Hour. I'm Chris Campbell of Contextual Electronics.
And I'm Zach Fredin of NeuroTinker.
Welcome, Zach, my old friend. How you doing?
I'm doing all right, Chris. How about yourself?
I'm good. Thanks for being on the show. Dave's obviously out this week. Sorry he can't be here. But I'm glad to talk to you because, well, I've known you for, 10 years now? Pushing 10 years? Maybe a little bit less.
2004, I think? 2004. Wow, 2003. Yeah. Fall of 2003. Yep.
Wow. Yeah.
Yeah, it's been a while. We went to school together.
Oh, yes, we should say
college.
That. Yes.
Yeah.
So me and Zach have known each other, and I have watched with glee as Zach and my worlds have kind of collided. You actually didn't start in the electronics world, but then you are now, well, you're just a superstar around here, and people might not know that you're doing this stuff, though, so that's why I wanted to have you on, and I think you're doing some really interesting things. So why don't you tell me a little bit about where you come from and where you're going?
I appreciate that. Thanks. My background isn't formally in electronics. I was kind of more of a hobbyist growing up. But I mentioned this to you earlier. I studied metallurgy when I was in college because I learned how to solder when I was younger, and we studied phase diagrams and learned about eutectics and all that. And I thought it was very interesting. So I got back into electronics with this NeuroTinker project. So that all started. Do you want kind of the whole story? Like, do you want me to give you the history of where we come from and all that? 5 minutes sort of deal?
Sure. Yeah, do it.
Okay.
Makes it easier on me, man.
Yeah. So, go back 3 years. My wife's an architect. We live in Minneapolis, and we were having brunch with a bunch of our architecture friends. And a guy named Andrew Salveson came to brunch. He was another architect, and he had done a project for his final project for grad school, where he wrote a plugin for SketchUp in Ruby that would essentially make a bunch of boxes in SketchUp. So SketchUp is like Google's solid modeling program.
Formerly Google's, now Trimble. Yes.
Okay.
Yeah, they sold it out. Sorry.
Really? Didn't know that. Okay.
Okay.
Well, anyway, so he was interested in neuroscience. He was interested in how he could connect that in with design work. So he wrote a program that basically instantiate an arbitrary number of boxes in SketchUp that can then connect into networks, and then each one of those boxes would behave like a biological neuron. So you could send signals through this network, and then the output of that network would be used to define various dimensions in the model that's kind of kept off screen. So he used it to make neuro-derived architecture, essentially, as kind of an exploration. So it's very abstract and very interesting. And he was kind of telling me about this at brunch, and I was like, "What's a neuron?" So it turns out neurons are we have 86 billion of them in our brain, and they're little processing cells. Yeah, that's it. Just 86 billion, give or take a couple billion or whatever. And they're basically just threshold detectors. So you have like an internal membrane potential, and that membrane potential is affected by external stimulus. And once that membrane potential exceeds a threshold, it fires what's called an action potential and sends signals downstream. And what's important is that, if you don't exceed that potential, the neuron doesn't fire. It doesn't fire until you actually get above that threshold. And there's all sorts of ways that inputs are weighted, and the whole membrane potential concept is based on sodium and potassium channels and ionic concentrations, and it's fairly complex, but you can kind of distill it all back into this basic idea of threshold detection. So he thought that was really interesting. He built this model in SketchUp that would have these little boxes changing colors to represent the internal membrane potential of each box as if it were a neuron. I was like, oh, that's really interesting. And he was like, yeah, and I want to make it, I want to make it into a physical thing. Like, I want to make Legos for neuroscience. Yeah, that sounds really neat. And be able to connect them together in a modular way and just kind of see how information propagates through the network. So me and Andrew kind of started on this without really an intention of bringing it into the educational world. It was more just an exploration. But because we were doing it on nights and weekends using our own money, we wanted to make it really cheap. So, kind of came up with some basic requirements: how many inputs, how many outputs, how we do indication. Distilled that down to the cheapest microcontroller we could find, which ended up being an AT-Tiny 44A, and spun up about, I think, 120 boards. So that would have been in the spring of 2014. So we spun up 120 boards and then reflowed them in a toaster and kind of did that whole deal. And then me and my wife and him and his girlfriend got a crimper and some wire strippers and like made this little assembly line in our dining room and like assembled all these axons, all these connector cables that would allow you to form the network. And then somehow figured out how to get all the programming to work. It was all very neat. It was all very like blinky and kind of abstract. And you could take 20 of these boards and you could build a network that you could then inject signals into, and it would do unpredictable things. So each processor is very simple, but they're also completely asynchronous. And they're all, everything operated on timer interrupts or pin change interrupts. So it was all like very responsive. And each one of the boards used the internal RC oscillator of the chip. So each one was a little bit different. So you had all these things that would make the network behave in strange ways. And
does the RC thing actually replicate? I mean, is that, I guess, neurons wouldn't be synchronous either, right? So.
Yeah, they wouldn't. They would have different time constants. The more important thing is they have different weightings. So the weightings of the inputs are what really change. So when you're learning things, you have new neural connections that are being formed. And then you also have the relative weightings of different connections that are kind of changing constantly as you learn new things. That's what we wanted to emulate. And then we kind of backburned the project for a little bit. Andrew ended up moving to New York City and joined a fancy architecture firm out there. And I worked on some other projects, but I ended up publishing all the documentation online. We open sourced the whole thing and put it online on Hackaday. And I got an email, would have been 2 years ago, from a neuroscientist at Boston College. So he was a neuroscience professor, and he told me that he was basically working on the same thing as a teaching tool, but he was like, what he said, 10 years behind where we were. He was using Arduino boards and like trying to get a single one to work, and we had made 120 of them, and this is super cool. I want to use it in my classroom. This is great. We should start a company and we should make this a thing. Which was crazy.
Okay.
Yeah, I mean, so just for context, I was at the time I was a sales engineer. I sold process instrumentation and control valves. So like, you have a grain silo in rural South Dakota and you want to know how many beans you have in it. Like, you put one of our radar transmitters on top of it and it sends a 4 to 20 milliamp signal back to your PLC, and you have a little display and all that.
Which is pretty cool too, but yeah, not quite neurons on a board you made yourself, right?
So our radar transmitters were pretty awesome. They Chris, what frequency do you think they operated at?
For radar? 28 gigahertz.
72 gigahertz.
72 gigahertz. Yeah. I should have guessed that because that's what what's his name? Sharvat does and Tony does. A bunch of the radar weirdos who have been on the show in the past. They all do that
awesome.
stuff.
Didn't know that. Well,
Tony Long. He does that stuff for fun. That's great though, right? You've got a story right here about something you're doing for fun that turned into something crazy. So
yeah, but doing radar stuff.
God bless y'all.
That is awesome.
yeah. No, it's really cool. Anyways, go ahead. Sorry.
Yeah, no worries. I could talk about process instrumentation for too long, so we should get back to this, I suppose. Where was
you
I?
were doing that though? You're saying that it was far removed from
what I was doing. Yeah, exactly. So I got this email, and I remember reading the email and looking at my wife and saying like, "Holy crap, this is crazy."
That is weird. Yeah, no, I talked to people about. So I talked to people at Hackaday about that stuff too, and I think that that's really great. Like, that is a success story, I think, and I'm not sure how many times that's happened or how common that kind of thing is. Honestly, I greet those emails with skepticism normally.
Yep.
So the fact that you didn't is, maybe you did. What was that like at the beginning?
So what happened actually? I think the thing that really closed the loop is that I Googled his name. His name's Joe Berto. He's now my business partner. I Googled Joe Berto's name, and when the Google search results came back, the first listing was his Boston College bio, and
that
the link
can be faked.
No, so the link was the link was purple because when Andrew and I a year ago had been thinking about trying to like see who else was in the world of neuroscience generally, like we happened to have been like just searching for neuroscience professors to talk to.
That's great.
And his name popped up, and like I didn't clear my browser history for a year, so like, the link was still purple. I was like, "Why is that link purple?" And I clicked his name, and I recognized the picture. I was like, "All right, this is weird."
That's great. No,
so
it's really great.
It was interesting enough that I flew out to Boston and met with the guy. Helped that I have a friend at Boston Dynamics, so I was able to like squeeze in a visit to Boston Dynamics and play with robots for a while.
I know that guy too.
Yep, you do.
Yeah, I got to meet those same robots, and that. For people who don't know, if you know someone there, get there as fast. Like I don't know if it was special that we got a tour, but man, that was
we went
magical.
on on a Sunday, and we were just able to spend a couple hours. And
did you ride one of them? No.
Didn't ride one of them.
I know.
Got to get pretty
on a Sunday.
pretty
I'm not sure. Yeah.
Didn't get to see any of them run. I heard that was back before the latest iteration, back when they were like really really loud because they all had to have these like onboard power systems, that were like gas powered hydraulic motors and all that.
Right.
So I didn't get to see them run, but it was still neat. Anyway, so went to Boston Dynamics, and then the next day went to Boston College, met with Joe Berto, and we like sat in a conference room for like 4 hours. And we drew this big Venn diagram on the board that was just like two giant circles that like barely intersected. On one side, it was like Zach tinkers with electronics, knows how to solder, like already built a bunch of stuff. Joe, actual legitimacy in the world of neuroscience, like has been in a classroom before,
knows
understands
what he's talking about.
Yeah.
Hey, like let me just say up front, you sounded like you knew exactly what you were talking about when you were explaining neurons before. So that's pretty good. Yeah.
Everything I know about this project is what I've learned because I had to like make neuron simulations accurate. Turns out when you need to make an accurate simulation of something, like you have to learn a lot about it.
Yeah.
So it's
called fake it till you make it, I think, right?
Exactly.
I've been doing that my whole life.
Exactly. But yeah, so we made this Venn diagram and like had this very narrow intersection where it was like neuro tinker. I don't know if we come up with a name then or maybe a little bit later, but and the neuro is obviously Joe and the tinker is obviously Zach. So we kind of came up with it that way. But great. Then so that was like February of 2015, and we we're like, all right, we both have to have full-time jobs and we have mortgages and things, so like what do we do? So he was familiar with the SBIR program, Small Business Innovation Research Program, which for folks that don't know is a grant program that's funded by the Small Business Administration in the US, and it's designed to stimulate the creation of small businesses that are focused on very high-risk, high-reward technologies. And what's interesting about it is that they devote $20 billion a year to this, and they don't really tell anybody much about it. So it's pretty close to the amount of like seed funding that's available, from angel investors and all that. I mean, it's kind of in the same order of magnitude, only you don't have to pay grants back. Like you have to tell them how you're spending the money, and you have to like, you're legally obligated to do so, but like it's not an investment, it's a grant. He was familiar with that program, and then the SBIR then filters down through different agencies. So we applied for we basically like went on a couple agency websites. So first the National Institutes of Health, we found a grant proposal for like a STEM education gaming thing. So we applied for that one, didn't get it. And then and
that's an interesting point too, because I remember when I first heard about SBIRs, I was interested that they weren't open-ended. I was always like, oh, well, why wouldn't they just fund research that people propose? But it's that basically like you said, the institution, like the what was the one that you first applied to?
NIH, National Institutes of Health.
Right. So like they have someone internally who's like, what would be really great, and then they put that out there, right?
That's exactly right. Yeah, they have a series of prompts. They have like a series of RFQs essentially that they put out that last for a couple of years, and it's like every May, like May 15th is the NIH deadline for their SBIRs, and it's like you have 20 different categories, and your thing needs to fit that category. So that one was called the official prompt was Serious STEM Games. So it was like science, technology, engineering, and math games like brought to the classroom. So it was a neat idea. We actually we were able to partner with the guys at MIT Game Lab to like write our proposal, and like I think we had a pretty strong idea, but I don't think we had really thought through the gamification that well. I think we had just been like, oh my god, this is a grant thing we could do, and like
hey,
it is a game. Of course, it's a game. Yeah, like Legos are a game. So then we we kept looking. We actually didn't hear back on that one. We until after the deadline for the next one we were looking at, which was through the National Science Foundation, and they had a grant called Educational Applications. So it was just like a general educational science grant program, for novel technology concepts for education. So we applied for that one too, and we ended up getting it, which was crazy. It was like we applied in June, and then we didn't hear anything for 4 months, and then we got an email in September that was like, hey, we need you to answer these 10 questions. We got the email Friday at like 6:00 in the evening Central Time, and they were like, we need you to answer these 10 questions by Monday morning. Like literally, it was like they were like, these would be like the essay questions, in your high school, and you're like, all right, you can't just fill this in. You need to like write 2 paragraphs about it.
Right. You need to spend all weekend basically.
Yeah, and what was really interesting is like the NSF is all about, with the SBIR, they're trying to commercialize technology. Like they don't want you to just be fed by the government for the rest of your life. It's like, no, we're trying to kick you guys out of here.
Grad students for that kind of thing.
Yeah, exactly. So the grant director wrote us this email that was just like, look, you guys need to dig more into how this is commercially viable, and you need to tell me what my return, like how I get my return. And we were like, what do you mean? He's like, my ROI.
do you want a kickback?
Exactly. It's like, no, like they consider their ROI to be the tax revenue they get from my employees 10 years down the road. They're like, that's how you need to quantify it. Which, I mean, like anytime you do like a pitch competition or you talk to investors, like you always put together this growth plan with revenue and all that other stuff. And so it's kind of
but that's usually a direct thing for investors. They want their specific money back.
They want to figure out how they can kick you to the curb and leave in 5 years with all their money, as opposed to like forming a sustainable, profitable business.
I'm sure sorry, if Avidan's listening,
inappropriate.
No, I think Avidan hopefully was different.
But it's totally different.
Yeah, no, I've seen stories too. So yeah, it's a different model though. You're saying in general.
It is. They're really interested in, and the other thing is that they're interested in stuff that isn't really fundable any other ways. I mean, we were like, we want to create electronic neuron simulators for teaching people about neuroscience, and like we talked to a couple of investors about that, angel investor types that would be the folks that would be looking at funding things at $200,000 for 6 months to see whether or not it's feasible. And they were just like, interesting. Well, let me know how that goes. I'm like, oh, great.
You should go on Shark Tank.
Yeah, perfect. The sharks would just love talking about neuron simulators. Yeah. So that was cool. So anyways, yeah, September we started hearing answers, and then like went back and forth a couple times, and then was it like November or December 20th we got our formal award letter, and our grant start date was January 1st, so we like quit our jobs and went full time. And that was January 1st of this past year. And the grant. So
I don't think this is this normal? I mean, like, did it having a professor? Had he ever done that before? Is having his like pedigree important?
So he had applied to one previously and he was not successful with it. But generally, like when people ask me that, I'm like, no, I don't have a PhD. I'm not an electrical engineer. I just built something that people liked and supported.
No, I'm not talking to that. I'm actually talking about the people that are in the audience listening right now who are grad students or PhD students, and they filed 300 applications for funding and nothing came back.
Okay,
I mean, you did two.
So talk about like talk about how to get these grants. So the SBIR that we applied to has an acceptance rate for that class. It was like around 12%. 12-13%, something like that.
Well, that's not bad, actually.
It's really not. And like that was actually on the low end. The previous class I think was more like 16-17%. So the things that you need, the grant has there's like a window of time you could submit your application between like mid-May and mid-June. And before mid-May, you need to write an email to the grant director. It's like one guy or one man or one woman like sitting in some office in Bethesda who is the grant director for that program, and like write them an email and tell them what your idea is, and they will get back to you within 45 minutes because that's their job, and they will set up a conference call, and you will talk to them for half an hour about your idea, and they'll be like, yeah, you should apply for the grant. Or they'll be like, no, you shouldn't apply for the grant. Like, that's not a good fit for my program. Like, they'll just tell you whether or not it's a good fit.
But it doesn't say that on the application. So you're saying that this is
if you read through like the NSF recommendations for how to apply for the grant, it says email your grant director. Here's his email address. But make sure you email him before he starts to get all these applications in, so he actually has a chance to talk. Like they make themselves completely available, but like a lot of people just throw an application out there and don't have the conversation.
So this is like a professor office hours kind of thing, where it's like, hey, I was here the whole time. You're the one who didn't come in until 2 hours before the test, right?
Yeah, that's it. Literally exactly what it is. So email the grant director, let him know, and get on the conference call with him. And then the other one is letters of support are incredibly important. So they're like really limited. You can only submit 3 letters of support per, for the phase 1 grant. And like, you should have a letter of support from someone that says, this is an excellent idea, and if it's successful, I want to buy this many of them, and I represent this percentage or like this size audience. Wow. And you need like so you get a letter from a potential customer, you get a letter from like, in our case, someone who thinks it's technically feasible to do it. Like, yes, this is I have been in neuroscience for a long time, and I could see this, being possible to simulate. so like you have to build this credibility, and based on the people you get your recommendations from. So like one of them we got was a neuroscience professor, and one of them we got was like I don't know if it was a superintendent. I always say Super
Nintendo Chalmers.
Oh man, now that I'm in like the ed tech world and I meet a superintendent, it's really bad.
Have you said that to someone who's actually a superintendent? You're
almost.
Like
almost
really?
Because before I meet them, I'm always thinking about that line. I'm like, Super Nintendo.
Don't say Super Nintendo.
Like, so it's gonna happen at some point. I just know.
Oh my god! Oh, you gotta start filming all your meetings or something.
Make sure it's like a small district or something. So letters of support, and then like just making sure that you dot your I's and cross your T's on like what the application wants. There's like a 2-page checklist. That's your application is 60 pages long, and there's a 2-page checklist that's like, make sure you have this, and this. Make sure it's not over the page limit. Make sure just like make sure you follow all their bureaucratic requirements. I mean,
RTFM is what you're saying.
Exactly. Because I think a lot fail because they don't get that. And if you pass a scientific merit review, or you're like in the top half of the respondents, like if they convene their committee and they're like, hey, this is not absolute garbage. I shouldn't say that.
You're saying that 90% is showing up, right?
90% is showing up.
Showing up with like a finished application.
You can't see this
that
with the
looks
microphone,
decent.
but my head's in my hands because I think I didn't mean to insult anybody by saying that. What I mean is that
no. I mean, what I heard is that you're saying that some people just chuck it out there because they're chucking it out to everyone, right?
Exactly.
They're just spraying and praying with grants.
Yep.
And so I don't think that you said something bad there.
Okay.
If you did, they're idiots anyway.
Yeah. Well, and the point is, if your application is halfway decent, you will hear something back. They'll tell you why they rejected you, and then you apply again 6 months down the road.
That's really nice. I mean, I wouldn't expect that at all. Honestly.
It's awesome. Yeah, totally. And it's a pretty broad ranging program. I mean, it's Small Business Administration, and they define a small business as any company that has less than 500 employees. So yes, it's not only startups. There's also large companies what I would consider a large company, with 480 people, where they have like 2 guys that are like, hey, we want to do this in a year, so let's submit an application for it, and they're able to do that.
Yeah. And it gets crazy too. I mean, I remember the first conference I ever went to. I was watching this talk, and it was this guy talking about like a wireless sensor was measuring acceleration, but it was mounted on a friggin' like Apache helicopter's rotors or something crazy like that. And he was in stage 3, and so he was getting like millions of funding, and because it was a military project too. Obviously, there's high costs there, but I mean, like that was my first. I'd never heard of that before, and I was just like, my jaw was on the floor, like, holy crap, there's a lot of funding out there for this kind of stuff.
And a lot of I should say that essentially every other category of grants so we went to this NSF conference where they convened all the people in our SBIR cohort for phase 1. It was like 200 companies, and of those, 20 of them are educational applications, and we were definitely like the bottom 20 in terms of like, this is a badass thing that you're building. It's like, oh, we're building this app to like do blah blah blah, or we're building electronic neuron simulators. And then there's like the optoelectronics group that are like, yeah, we're building like optical phased arrays to do blah blah blah. It's
eyeballs. Like, oh cool.
Oh my god, yeah. You sit down at this conference, you're like, so what are you guys working on? And it's like, whoa, just you hear amazing stories about this
great.
stuff. Then of course you're like, yeah, I'm doing laser stuff and surgery stuff or whatever.
Is that invite only? How did you get to that?
Yeah,
conference?
So it's like their phase 1 boot camp. So it's only owners of the companies that got phase 1 grants.
Okay, because I mean that sounds like that would be like, just to hear the ideas kind of stuff. That would be great. Or are you guys listed somewhere online that maybe the other people are too?
Yeah. So anybody
curious.
that gets an NSF grant, anybody that gets any of these grants, it's publicly listed. There's some maybe not great website run by the official government that does it, but there's also a lot of people that scrape those websites and put it into a much more searchable format. And I know this because like as soon as we got the grant, we started getting all of these like snail mail things. Yeah, oh my god, so much mail. Like, oh, Neurotinker, you do this. Oh, we want to help you.
Right.
So yeah.
Right, like when you buy a house too, where it's like, do you need moving help? Do you need landscaping?
Yeah.
Exactly.
Oh my god. So
you're listed.
Yeah. So
somewhere.
we got the best one was we got a trademark on our logo, both the name Neurotinker and the name Neurobytes, but also we got a trademark for the graphic design of our logo. And we started like 2 months after it actually went out in the USPTO Gazette. I started getting these like, snail mail notes from like all over the world that would have like a really poorly cut out photocopy of my logo like pasted onto this letter that was like, we want to help you get trademark protection in like Uganda or whatever.
Oh man, enterprising individuals. Let's just call them that, right? That is
It was
nice.
interesting, yeah. So lesson learned.
I was always surprised that I've got a design patent, and thank God I moved. But at my old address, at least, I was surprised there was never spam from that. I always figured there would be. Like why wouldn't recruiters look at that stuff up and be like, oh, engineer?
Yeah, totally.
Like,
I'm surprised you didn't either. That's interesting because it's calmed down a little bit, but I think whenever the Gazette, because they like publish this USPTO Gazette that has like all the new trademarks and I assume all the new patents in it. And it's like, it's got the mailing addresses, like it's all public information.
Yep. Oh yeah. Yep. That's why you get P.O. boxes, folks.
Lesson learned on that one. Man, big mistake, Zach. Yeah.
So you guys got a stage 1.
Yep.
That's great. Congratulations. And I remember when you were talking about it on Facebook, and you were just like, "Hey, I'm quitting my job." That's new.
that's different.
Yeah. But so what comes after that? So I mean, stage 2, stage 3, is that? Are you guys like what's the requirements for that?
So we finished our grant. We finished up at the end of June. And you basically you get this chunk of money and you have to spend all but 7% of it by then. You get 7% that goes towards the capitalization of the company, that you can kind of use towards whatever. And we what we learned talking to people was they're like, you want to keep every penny of that if you can, because if you want a stage 2 grant, like they're going to put you through this audit to basically say if you're like see if you're financially solvent enough to support a larger grant, because you need to have enough money to get the credit and to like just support all the administrative stuff. So we really didn't want to spend any of that. But what we were able to do is do a pilot run. We were able to fund a pilot run and sell a handful of kits into a few different classrooms, which is pretty cool. So we now have a user base of like, I don't know, 20 classrooms between high school and college that have the latest Neurobytes kits. So that's what we've been doing for a lot of the last couple of months, is like following up with those people and seeing what their experiences are and working with them to build curriculum and so on and so forth. And we're like in the very final stages of our last audit to get our phase 2 grant, which is really exciting. So I really wanted to come on the show.
I get
on the show and be like, yeah, we're gonna get our phase 2 grant, and we passed our merit review like 2 months ago, and we're going through the audit essentially right now, and like any day we're expecting to hear something positive back. And our plan with that is that's going to get us through the rest of development and through commercialization.
Okay. And so the plan is always to take people to stage 1, stage 2, stage 3 as well. I don't really know this stuff.
Yeah. So at least for this program doesn't have a stage 3. NSF just does stage 1 and stage 2. But when you apply for stage 1, they review your application as if you're going to apply for stage 2 as well. It's kind of expected that, like, in our case, like, well, we got to the end. A lot of people get to the end of stage 1 and like they still are working on their MVP, and we're like, we got to the end of stage 1 and we're like, we just finished our 10th prototype iteration. We made 500 of these things and we sold them to like a bunch of classrooms. So like we were pretty far ahead of the game. Right. But basically, and
then they're like, Zach, come on, man, we're making eyeballs.
We're doing cooler stuff than you. Our stuff isn't just like a little circuit board.
No, your stuff's really cool, actually. And actually, we will need to link in videos and stuff of yours working as well.
Okay.
That is definitely we'll have to do that at some point.
Yep, I will find some good videos. Hopefully, we have those. Yeah.
So, could you tell us the relative amounts if you don't mind? I don't know if
it's no problem. It's all public too. Our phase 1 grant was $150,000, and the phase 2 grant is $750,000.
Oh wow! Okay.
So and it's over 2 years. And for us, our phase 2 grant supports myself and my partner and renting space and doing a whole lot of prototyping. And we're also funding a series of curriculum development workshops this coming summer, and like hiring an intern and working with a number of different contractors. And so there's a when you put the grant application together, you basically like have to lay out an array of buckets, and you're like, this is the relative size of these buckets, and this is how full I need each one to be, and like this is what I'm going to spend them all on. And then if you screw that up in like 2 years, you're like, oh my god, I needed more in this bucket. You have to like submit 10 pages of paperwork, but it is possible. I mean, as long as the money's allocated, you're able to have some flexibility. They really emphasize that like we are the government and we do run slow and we are bureaucratic and all that, but like we also understand that you're a startup and like you may need to, like, they used the word pivot like at our workshop. They're like, you may need to pivot. I'm like, do you know how much paperwork that probably is if we have to pivot? But they said the word, so we're like, all right, they're on the same team as you. You just have to like kind of be willing to go through all the headache of it.
Well, that's encouraging though. I mean, like, so honestly, like I said, I had a very limited experience with SBIRs. After I went up and talked to that guy after the fact, he's like, yeah, only people who've ever done these before get them. And I'm like, well, how does anyone ever get started then?
Yeah, so here's something I can offer to your listeners, and it's something that Joe and I have decided that we're willing to do. When we were applying for a grant, the most frustrating thing was that we had no idea what a grant application looked like, which was like, it's crazy. Like, a lot of people get these grants every year, and like, you will never find like a successful application online.
Just publishes one online.
So if anybody wants our grant application to see what a successful SBIR grant application looks like, send me an email. Zach@neurotinker.com. Let me know. I don't want to share it publicly, but we have sent it out to many interested people that just like want to see what sample grant is. I can't share it publicly because it does have some names in it, and I just shouldn't publish that. But I'm more than happy to share it with any interested parties.
I'm always surprised when they don't do that with like even formats of what they're looking for. Maybe that's too constrictive or something. But like it seems like that would just lower their headaches too. But whatever. Okay. Well, that's a very nice offer. That's very good. That's great of you.
Hopefully it helps someone out.
Yeah. Okay, so $150K to start with. That sound, as we talked about, I think when Avidan was on, he said they'd give $500K as a seed investment, but same kind of thing. It's like, that's with hardware, that's not that much money actually. I mean, like that goes pretty fast.
Yeah, it does.
So you started getting into manufacturing. What was that experience like for you?
So we it was hard. I mean, it was really difficult. We had to figure out. We had to be really careful about what our quantities were. So the biggest pilot run we did using phase 1 money was 500 pieces, and it was kind of the first board that I didn't put together myself in a toaster oven. I actually worked with the contract manufacturer and had them source the PCBs and actually source all the components and do all the assembly and all that stuff. And we wouldn't have been able to do more than 500. and
you're just saying cash flow.
Just because of cash flow, yeah. I mean, just because of what our costs were. And for our phase 2 grant, we're not expecting to do many more than that either. I mean, it's really just, and you're really not allowed to either. Like, you're not allowed to fund a production run using the grant money. In our case, we were allowed to like fund a pilot run, and then we got permission from our grant officer to like sell a couple of the boards as a means of demonstrating our commercial potential.
And then you roll that back for more boards after the fact.
Yeah, but we're not allowed to like, take that 750K. Like, well, let's earmark 150K of it for the end of phase 2, and we'll just like do a big run, and that'll be like our kickstart. You know, like you can't do that.
Yeah.
That's really the challenge. And one of the things we've talked about, and one of the things they encourage, they have this phase 2B program where like they'll do matching investment. If you find an investor, the NSF will match those funds.
That's pretty cool.
If you qualify and so forth. So that's something we've talked about. Is like, well, maybe we will need to take on private investment at the end of our phase 2 period so that we can spool up a production run. We also have like talked on and off from the probably since I don't know, like 2000, 3000 BC or something. Like, we've been talking about it forever, like about doing a Kickstarter campaign, and we just keep pushing it off because we're like, it's kind of a big distraction at this point, and we don't need to do it, so we're not going to do it.
Right, you would both switch into marketing and PR mode, and that sucks.
Well, and so a weird thing about the grant is like it's an R&D grant. You can't spend the money, aka you can't spend your salaried time on sales and marketing.
Oh wow, okay, so that even includes time. Oh, that's interesting.
Yeah. Well, because like we have to keep time cards. We're a government. We're on a government contract. We have to have a time card. We have to like print it out. We have to sign it. We have to do all that stuff.
Yeah, I was wondering about that too, because you mentioned in the example of like selling boards. Does that money then go into a separate, like, do you have to keep two sets of books effectively of like, well, this is money that is unexpected income, like no one's actually expecting to make money.
We basically had to keep really close track of it, and we weren't selling. We were basically selling the stuff at cost.
Okay. Ugh,
so we weren't.
Though.
Yeah,
because then you're not really testing the market either, right? You're testing. I guess you're getting the product out there.
Yeah, but we're selling. In our case, we were selling it at cost for a pilot scale run. And the way our manufacturing cost kind of works out is like, well, we were able to test a few price points, and as we scale, based on we were able to get a pretty wide range of quotes from our contract manufacturers. So it's like, well, as we scale at these price points, like we will get this ultimate gross margin eventually.
Right.
And then Microchip bought Atmel, and the cost of my processor doubled, and that increased my BOM cost by 10%.
Aha! One of the casualties. Did you see they changed it?
I know nothing about that world. It is probably a coincidence, but I just remember like looking at those DigiKey prices back in February, and I was like, ooh, 45 cents a piece, and like now they're 89 cents a piece. In the same quantity. Right. So, for all I know, it's like the AT Tiny 88, which is the chip we are using now. Like, it probably goes into some automotive product that, just happened. Oh, we're not making that anymore, and like global demand for them.
Sourcing stuff. Yeah. No, that stuff gets weird no matter what. But still, like the correlation in your brain is.
It's really fun to blame that. To blame the acquisition on that. It's like a really convenient target, so that's what I use.
Yep, good. Everybody needs a source of ire, so.
Yeah, exactly.
Okay, so let's talk more about the manufacturing stuff. So you said 500 pieces, single micro on board, so you're not getting more than 500 pieces. That's pretty rough right there. So you're not even buying a whole reel.
Yeah.
Does that mean that you, are you getting any kind of volume discounts at all, or no?
Yeah, 500 pieces was when I was selecting a contract manufacturer. My first priority was like I wanted someone that was local, because I wanted to go actually be able to see them do the work. And this, it even sounds stupid to say it, but like I really just wanted to watch my boards run through the machine. And it was great because
I don't think that's stupid.
It was awesome. I was able to like go there, and they like the plant manager was amazing. He let me go in, and they like moved all of the like ITAR controlled stuff out of that area, so I was able to actually come in and videotape the run. Videotape
wow, that's nice.
the QFN package going through the X-ray and like videotape the pick and place going and the stencil printer and all that. So I picked this contract manufacturer because they're able to, they were able to quote me, a 50,000 piece run too in the same building. So 5,000 pieces was like 500 pieces was like at the very, very bottom of their capability. They're like, we are using our smallest machine and we are only running it for like an hour and a half to do this. So a good portion of that was non-recurring. There was like the non-recurring engineering and also just like, I know they built a lot in on the per piece price.
Oh no, of course there's that stuff. Did you think? I mean, was that a marketing move on their part? Did they expect higher growth, or did you just charm them into thinking? Because I mean, like it sounds like they're a medium to larger volume.
manufacturer. No, it was. So. I think it was a marketing thing on their part. I mean, they definitely took a bet on us, which I really appreciate.
Well, I think you're supposed to say their name now, Zach. I think you're supposed to give them some marketing.
Keytronic EMS, and they're based out of Oakdale, Minnesota, and they actually have a couple. They have a couple different branches around the U.S., but I use the one in Oakdale because it's 20 minutes away.
That's great. I mean, well, and I think you mentioned either before the show or during the show that there's a bunch of medical stuff too. So I mean, I'm guessing that helps at least to have local CMs, and everybody has that.
Yeah. So Minneapolis is like world headquarters, or maybe not world headquarters, but is a hotbed of like the medical device industry. So you have like St. Jude Medical and Medtronic and a bunch of other ones. I'll bet you have listeners that are employed by the other ones, and I'm forgetting them. Boston Scientific, that's a big one. I talked to any of the CMs around here, and a lot of the work they do is medical device oriented.
Right.
But that's that kind of works out because medical devices nowadays have a pretty wide range of quantity requirements. I mean, there's definitely electronic medical devices that like they're going to make 1 million of them a year, probably 500,000 of them a year.
Yeah.
So they just because they're doing high end stuff doesn't mean they aren't also built for reasonable scale, I would say.
Yeah, I would say the only downside would be if they had priced in like if there's any kind of like certifications they need to get, and then that's priced into everything they quote.
Yeah.
Like if they don't maintain separate lines and stuff like that for the non-certified, then that would be the only thing I would think. But I don't even know what I'm talking about with certified. I don't even know if that's a thing. I assume it is. There's some kind of ISO something.
Yeah, I think there's an ISO.
There's always
for
an ISO
medical
standard
stuff. Yeah.
Well, that's great. No, that's good. That is really nice to have it local. So, did any problems crop up where the local actually paid off?
Yeah. Actually, there did. I was like ready to turn the key on the run, and they're like, DigiKey's out of JST GH 4-position connectors. I'm like, talking about 6 months ago, I checked the inventory, they had tons of them, and they're like, wow, Zach learns his little lesson. So I had
6 months ago. Yeah, you bought them then, right, Zach?
Well, okay, yes, I did, Chris. So I did a 200-piece run in my toaster oven. Lesson learned there as well. Very tedious. I actually made a little pneumatic pickup tool with an aquarium pump. It works. Like I was.
No. I meant you said you needed the 500 pieces or whatever, however many.
I'm getting there. So when I did the 200-piece run, the connectors were cheap enough. Like when I bought them, if I bought a large quantity of them, I just bought a whole reel, and I happened to have enough left on my reel that I was able to bring. I drove it to the plant. And so I this is the other reason these guys are amazing. I called the the person that quoted me the project. And I was like, look, I don't need all 500 of them right now, but I really need 100 of them because like the University of Minnesota just they bought a couple kits and like I need to. They're starting their class next month. Right. So these lead times aren't going to work, and they actually agreed to like take the reel that I had, load it as a partial. So they had to like do all the retaping and all that, and like load it on the machine. They ran 120 boards for me, and I was able to get them to the school. I was able to deliver them for the kids, Chris. It was great.
Was it before Christmas? Did you make it?
It
before
was.
Christmas,
I got it before Christmas, and then they just followed the standard lead time on the rest of the connectors, and they ran the balance of the run, and they didn't even charge me for for breaking the run up into two parts, which is just amazing.
No, that's good. No, that's what you were getting to. I didn't realize that. That's awesome. So being able to get there and just have that relationship, that is very nice.
It's really interesting. It's and to be fair, I owe it. I don't know. I go back and forth on this a lot, but I know at some point I owe it to my investor, which is people like you, Chris, to get the best value. That was a callback to like you being a taxpayer and like me getting a grant.
Oh, I see. I see.
Yeah,
Thank you. I was like, I haven't. Did I buy a kit when I was drinking beer with Zach?
Nope.
Okay.
No, I mean, like we have a responsibility to like be financially efficient. So I do need to look at other ways of sourcing it. I need to look at going overseas and all these other things. But,
which is kind of counterintuitive too, because you'd think that they would build in something where it's like, oh well, value versus generating more tax base by manufacturing in the U.S. kind of thing.
Yeah, it's not really called out. I don't know. It's kind of interesting. And the other thing is like, you get all your prototypes made under the grant by U.S. suppliers. Then like as soon as you scale and you're out of grant, you just like kick it all overseas. And there's probably not much they can do about that.
Right.
So for me, just kind of simplify it and say like, well, I like having videos of the parts going through the pick and place and like being able to like shake the guy's hand and actually like turn the key on the machine and all that.
Right.
It was I don't know. It was in some ways an educational process for me, but then but ultimately like so we look at the cost of doing business with them and what the finished cost is for large quantity production, and we look at what price the market's shown it will support. Then we look at like what's in between those two numbers. And we're like, well, actually, we can run a sustainable business based on that. So like, why don't we focus? Like, it's pretty much just Zach. So like, Zach, why don't you focus on like actually writing firmware? Oh God, I hate firmware.
Well, actually, I wanted to ask about that too. So, okay, so this thing has an AT-Tiny 88, still the 88 on board, because I think I was trying to push you towards an F-Zero STM32.
Yeah, so we're actually looking at the STM32 F-Zero as a potential next generation board for a number of reasons. But the current product has the AT-Tiny 88, and it's pretty well tapped out in terms of its capability. So it's we have in neuroscience terms, we have 5 dendrites, so we have 5 inputs, and then we have 2 axon terminals, so 2 outputs. Each dendrite has a sense line to figure out what type it is, whether it's an inhibitory or an excitatory connection. So whether it lowers or raises the membrane potential. So you have 10 I/O ports on the input side, and then essentially 4 on the output side, because we wanted the flexibility to be able to toggle them individually. Then they each have 2 switches, and they also each have an RGB LED that's got to be PWM'd with 8-bit PWM, which is more PWM channels than the AT-Tiny has. So it's done in software, which is, I don't know. So that's another thing where if anyone takes a look at our boards, you'll see that aesthetics are somewhat important to us, and the LED in particular is important to us. It's a bottom mount RGB LED.
Bottom mount?
So
what is that? You mean like
bottom mount? Yeah, so it shines down through the board.
Which I didn't
allows
know that.
you to do kind of neat design things. It just really cleans up the look, and it also I have like a 3mm hole. It's right in the middle of our logo where the LED shines through, and I plated the entire hole through. Actually, Keytronics called me up and they're like, "You have the 3mm hole there, like it's plated through, like."
What are you doing?
But it looks great. So like the LED, like it shines off the plating and it looks really awesome.
Yeah,
like really improves.
So like, and you guys do have that impulse thing. So like when an impulse hits one of these little boards, that thing really friggin' flickers. I mean, that thing goes hot.
Yeah.
So I guess that probably makes it shine even more.
Yeah, and that just means like we have to make sure we have enough resolution, because normally the LED is running at like 10% brightness. And then when it flashes, I want to be able to flash it at 100%. So it's like really noticeable. And that was, I don't know, that's been an ongoing challenge for me. It's like every time I like update the firmware, I like grab a neuron and I wave it around and like see how far the dots are apart from each other. I'm like, that's not good enough. You need a higher refresh rate.
I see. Right. Yeah. Right.
So all sorts of reasons we want to move to a 32-bit platform. The math that we're actually doing, some of it would really benefit greatly from being able to count above 255. So something we're looking at. From a user friendliness perspective too, we're really serious about keeping this project open source, because we think someday it would be cool for someone that's actually like studying real neurons, someone that's actually a neuroscientist that's like in the lab using their probes to like probe the signals on an actual neuron, can try to emulate that in neurobytes, and then they'll contribute to our open source firmware, and they will,
right. So like profiles of
different neurons. Exactly. Like, there's Bruce Land on Hackaday.io actually sent me he commented on the project a couple of years ago and linked to a guy named Eugene Isakovich that basically in the early 2000s came up with like a really computationally efficient way to emulate all different kinds of neurons, like the fast bursters and like the all the other kinds. I don't know. And he like had a set of differential equations that you could plug different coefficients in, and it would like with those specific values would simulate XYZ type of neuron.
Yeah, that saying differential equation, it's like, oh yeah, you better get some floating point in there.
Yeah, exactly. So I actually I wanted to emulate. I wanted to actually run his program on our microcontroller, and I went down this like really really deep rabbit hole of like basically I wrote this like program that would iteratively optimize a set of coefficients around. I don't know. I got it to work on the AT Tiny with a specific set of coefficients, but it's not optimal, and it took a long time, and it's computationally difficult enough that it really affects the LED refresh rate, and it flickers, and then everything.
Oh, I see.
Doesn't look good.
Yep, that makes sense. Okay, so wait. So one more thing here. So now, so you have. So again, people are gonna have to look at a picture to see what you're talking about. But you basically have put in the silk screen and in the gold, or well, in the plating, whatever. Looks like a neuron in there. The shape of the board looks kind of like a key, where there's like a bulbous end and like a narrow end, right? But then you mentioned connectors around the edge. So then, what does this look like when they're all plugged together?
So when you're actually
how does one plug them all together? I suppose.
Yeah, when you're actually working with it, all the components and everything it's designed to be face down on the desk. So when you're looking at them, you just see the gold neuron shape, and you have the flashing light in the middle. To connect them, the connectors are all side entry locking JST 4-position connectors. So you kind of get a thumb and forefinger and squeeze the connector together and pull it in, or push it in or pull it out. And the cables are different lengths. So we have a stubby cable that's like 1.5 inches long, and then we have a longer cable that's like 8 inches long, that you can use red cables for excitatory signals, blue cables for inhibitory cables to form simple networks.
And is it built into the cable? Like, where is the coding built in? Is it in how you plug it in, or is it built in how the cable's built, or how do you actually tell which is which?
So as it stands right now, excitatory cables have 3 conductors. So they have power, ground, and signal. And then inhibitory cables have 4 conductors. So they have power, ground, signal, and type. And the type pin is just held high all the time. So the microcontroller looks for the type flag, and if it sees that, it identifies it as an inhibitory input, which is not the most efficient way to do it, but and then for inhibitory cables we made them blue, and excitatory cables we made them red, so you can physically tell the difference. But every once in a while you have a student that's like, why do the excitatory cables have one fewer conductor than the inhibitory cables? I'm like, excellent question, let's go on a really off-topic tangent about electronics for a while.
Yes, but I wanted to talk about the whole time anyways.
Excellent.
Right.
Yeah.
You get the really
it's actually pretty
curious
funny.
ones.
Yeah, I go into there's a local high school, Patrick Henry High School in Minneapolis, that I go into. I've gone into a couple times because I have an engineering teacher that I work with, and he's like, come on in and like talk about your startup and like teach them about neuroscience for a while. So we like talk about neuroscience. We have a little patellar reflex kit that's got like a 3D printed leg, and you build the neural network that like makes your leg kick when the doctor smacks it with a hammer.
Yep.
That's all well and good, but then like I get really excited when I get to show them KiCad and like teach them about schematic design and stuff like that.
Nice.
I'm indoctrinating those impressionable minds on using KiCad. It's great.
That's awesome. Yeah, well, I approve. That's good too, because I think, well, it's interesting from a lot of these perspectives where it almost could drive the conversation a little bit, right? I mean, like thinking about the tools that we used in biology class, right? Or the tools that we used in a lot of different classes, I suppose, in general. Like, there weren't many electronics demos, right? Even if they were simulating something else. So it could be kind of an end around to go and teach kids that, hey, electronics actually make this cool thing. I don't know. Like, I think they understand electronics are a thing, but not that they are tangible like you're doing. You know what I mean? Like, it's more like, oh, I have an iPhone, right?
Yeah, no, exactly. We, I think it was the Department of Education or some group within there did a study on like how we improve STEM retention. Like, kid graduates from high school and wants to study a STEM topic, and like, how do we improve the likelihood that they'll actually finish it? And one of the factors they found to be important was studying STEM topics in a multidisciplinary fashion. So like,
oh, that's great.
Studying engineering while you're studying biology, for example. So we're really keen to bring all that stuff in kind of as soon as we can. And what's neat is like, I would do this thing at Henry where I would I'd pass a Neurobytes board out to all the students. And I'd be like, all right, now flip it over so you're looking at all the little boxes and the soldery ball stuff or whatever, connectors, and like,
the black things
look at
and
that really
the silvery
closely.
things,
all the silvery things, the little purple buttons, and the little, the tantalum capacitor and all that. And I was like, and now look up at the overhead, and I would have a full screen, like, close up view of the KiCad, with just the copper, the copper layer on the back of the board. And they would kind of like hold it up and like look at the board, and like you would see like a series of light bulbs light up, and they're like, oh my God, like that's, what we're seeing there is actually exactly what I'm seeing right here. And then we go back to the schematic, and they'd be like, oh my God, and that's that. And,
I just imagine some of these kids failing their neuroscience final though, because they're like, oh yeah, you just hook things up in KiCad. That's how the neuron works.
Yeah, it's all about that. Yeah. And of course, not all of them got that excited, but we had a couple that were like, really
you filter like that.
That's
good.
Yeah,
that's good.
Absolutely.
I like that multidisciplinary thing too. If you have the source for that, I'd love to see the article about that.
Let me see if I can find it, and I'll send it over to you.
I've been saying one of my goals for the show this year is to do stuff where it's more, like we talked to a lot of people that are doing electronics and stuff like that, but I'm actually interested this year in getting people on the show that are like using electronics in their work, understand electronics, but then actually even need more help with electronics, right? So I mean, not that you don't, like, what you're doing here, but like I was thinking about like environmental concern stuff where they might need sensors or have new challenges, that kind of thing. Like, I am actually very interested in that. And if people are listening and they know of stuff like that, I'd love to hear about it. So just want to get that out there. I guess it is a new year.
Electronics, there's a huge opportunity to reach out to other parts of the community, like beyond the electronics community. It's like design, we're at such an interesting point where like hardware is so cheap and it's so easy to develop and you can do such amazing, cool things with it. It's like, there are more interesting applications than like any of us will ever figure out. Like we just need to get that stuff. We need to push it out as far as we can, and then someone that's like in some way far off field is going to find some crazy amazing application. And like that's where the magic really happens.
Well, I think the big thing is like we need the Zachs to meet the Joes, right? I mean, like you met Joe, who's already in this field. You understood the electronics piece, and then there was that you almost like need that as like the format for other teams where they need someone to be doing like hands-on hardware, but it's still it's obviously a very interesting application. So that's the stuff that I'm very interested in the new year, and hopefully we can find more people like your team like that. I think that's really cool.
Yeah, no, I think that's a great idea. I think your day job does a pretty good job of that. I do say so myself. You guys are doing great work over there.
Hackaday.io is definitely a good meeting place like that. I think there are more places that like that kind of stuff. That is the hard part, right? I mean, like I don't know where biology people hang out. I don't know where neuroscience people hang out, and well, I just joined a new hardware space in Chicago, and I did find out there's another. There's actually a bio startup place, so I'll probably go poke my head in there at some point.
Nice.
It's like a medical device startup called Matter around here. So.
Yeah, I think I saw that picture. I don't know if you like posted on Instagram or something. I think I saw a picture of that space though. It looked awesome. Dude. You guys all have like workbenches and stuff, right?
That place is so big. It's 63,000 feet. There's 10 different types of workshops. It is like and the fact that it started, like I've talked about it on the show before, but like the fact that it started right when I moved here is like, I mean, it's just like fate. That's crazy.
Yeah, that's so awesome, man.
If there are people in Chicago, we're looking for more people to join and more people to help build stuff, because it's like, oh, hey, we're supposed to open in 6 weeks. So yeah.
Oh, that's awesome. Well done. How many people will it support? Is it like a workspace for a couple hundred people at a time, or is it?
Yeah. Oh, yeah. I mean, this thing used to the facility itself used to have 3 full like the super long SMT lines. Where, it's just like pick and place after pick and place, then goes into reflow, then goes into...
like the giant Quiznos ovens and like
exactly.
Totally.
Quiznos ovens. Yep, Quiznos ovens. And so like it was 3 of those with full like it's just nuts. And so
they keep one by any chance? You guys hold on to any of the capital equipment from that place, or is it all stripped out?
They left a bunch of stuff behind, and
nice.
Not the line, but someone else. They actually brought in a separate company that's going to be doing in-house pick and place. So
that's fantastic. That's amazing.
I'm very excited. I think you'll have to just come down and visit. You're not that you're not that far, right? Just what, like
I will.
Flight?
Yeah. No, I'll just screw it, man. I'll just drive. It's not a problem.
I actually don't know how far away we are. How far is Minneapolis from?
We're like 6 hours.
Yeah, so that's like an hour flight.
It's not
like
bad. Yeah.
Cleveland to Chicago. Okay, so you mentioned the stuff you hate. Let's talk about that. What do you have to do to program these things? I mean, like, so you mentioned the math, but then the when you said at the outset of like the threshold seems like it's easy, but it seems like there's a lot of nuance there in terms of models and stuff.
Yeah, it's interesting. Like we started having bugs because we weren't listening to inputs the way we should, if that makes any sense. Like we weren't driving the inputs based on pin change interrupts. It's like, well, so we're missing an input by like a couple milliseconds because we're only checking it when this program loop goes by. But when you build a big network and it's all the information is shooting around asynchronously, it makes a difference, you know. So the timing thing becomes a big deal. I think the hardest thing we've had to consider were the connectors, though. Because I really wanted to be able to have something that was small. I wanted something that wouldn't dramatically change the form factor of the board. I wanted to be able to get 7 user-friendly connectors onto a board that's like, 30 by 60 centimeter or 30 by 60 millimeters or whatever. See, I'm trying to switch units a little bit. So
30 by 60 millimeters.
Yeah, so like that would be like 1.5 by 2.5 inches.
Oh yeah, okay.
Yeah, we want 7 connectors on there. Each connector needs to have 4 positions, and it needs to be able to handle. Yeah, that starts to
get pretty small. Huh?
Yeah, well, we want to be able to handle close to an amp if we can. So we're trying to use 26 gauge wire.
Wait, an amp? Why an amp?
Because we want to be able to make a really long chain of them and then put a servo on the end of it.
Jeez. And it's daisy chained. Okay,
it's daisy chained.
And these things are powered off the line, right? That's true.
Arbitrarily daisy chained as long as someone wants, and you need to be able to power it from anywhere in the network, and then and there's a motor mode that converts one of these things to directly PWM, a hobby servo. So it's like, well, now you have like a 300, 400 milliamp load at the very end of this chain.
Oh my god!
So it's kind of been like this design exercise that has to go all the way back into what is the intended neuroscience circuit you're building? Like, does it make sense to ever build a chain that's like 30 neurons long that ends in 5 motors? Like, well, if it doesn't, we don't have to design around that. But we still kind of are.
So you're kind of defining the limits of the solution space, right? Because then you can list that of do not do this, this, and this.
And we really don't want to put any limits on the actual users. I don't want to have to tell them don't connect them this way or something will catch fire. It's like, well, and that'll happen,
So and also those things. So I remember when you showed it. So you guys were demoing at Maker Faire.
Yep. Yeah.
There was a loop as well. So how does that end up? Does that affect the power, or is the power only going on one pin, so it doesn't really matter?
Yeah, the power just kind of feeds into the network in one place, and you're gonna have some voltage drop as it goes from place to place to place to place. And once you build a really complicated network, calculating what the voltage should be based on all of these different connections becomes the resistor grid problem from school. It's well, let's just plug it in and see if it works at some level. So one of the things we've done is we put regulators on board each device, so that we can handle a 1 volt drop essentially maximum.
Oh, wow. Okay.
Which kind of that accommodates a lot. But so the challenge I had with connectors though is that any connector that's not designed to be consumer facing, that's not a micro USB and not an 1/8 inch phono and not XYZ, like the board to board connectors that I wanted to use, they're never rated for more than 35 to 50 insertions because the manufacturer designs them as an assembly aid. It's like, in 10 years, if you swap this board, like you're gonna have to unconnect it once and then connect it back in again. And they in some cases they'll design them so that like this connector can sit around for 5 years in like maybe a non-ideal environment, and when you connect it, it'll connect aggressively enough to scrape off all that corrosion and like work the first time and still hit our resistance, measurement. And as it was explained to me, it's like, well, sometimes that aggression, comes at the detriment of long-term reliability. Because like now you plug and unplug that thing and it's like, there's no oxide layer left to scrape off. Now you're just damaging things and loosening it up. So I had a lot of conversations with JST. I've gotten to know my local value-added reseller who I use to actually buy my cable assemblies now. I bought the crimper and I crimped a lot of cables, but now I pay someone to do that.
That's smart.
But I also have gotten to know the JST regional rep. We actually have a JST regional sales manager that's local to Minneapolis because they do so much business in medical devices. So I can talk through him to the factory and talk to the local guy and of course, like every conversation I have, they're like, no one's ever going to tell you it's rated for more than 50 connections. And I'm like, come on, man. Like, what connector can I use though? And they're like,
well, you could wait. So you're doing what, gold flash on that?
I'm not doing it at this point. We're not doing any of that. They're just the standard ones, which I think have like a nickel plating on them. So I'm actually getting a sample of the gold flash ones later this week. Tomorrow.
That's the thing though. Like the gold stuff, that'll wear off real quick.
Well, that's the thing. Yeah, I could go gold flash, and it's like not that much more expensive. But gold flash is really like corrosion resistance before you plug it in that first time. It's like, well, or you could do gold plating, and like those connectors are 3 times as expensive, and the connectors already represent 30% of my BOM, which is crazy. The connectors are...
Okay, so I'll ask the a-hole question. Why are you still using branded JST connectors?
That's a fair point.
Only because I see the same thing. So like the most of the time when you see people using like those lithium-ion batteries, also because I see a lot of search results too in my work, and there's this like one brand that's really like, it's got this obscure part number, but you just see people searching for it all over. I mean, it's not even like that this is secret inside stuff. You could see this on like if you go to Find Chips, we show a lot of the searches and in like popular searches, and it's in there. It's just like these are parts that people are searching for because they need. It's the same problem you're running into of like low cost stuff, low cost connectors.
I guess part of it is that the failure mode for my connectors will be kids getting frustrated and throwing it in the trash. Because it'll just be like an intermittent issue. Like every once in a while you'll plug a certain cable into a certain neuron and like the light won't turn on, or it'll reset the microcontroller, or it'll do something weird. So I have like a really there's a really high risk of severe customer dissatisfaction if we have issues with the connectors that are intermittent. I mean, if they break one off the board, like it almost never happens, and when it does, it's very clearly cases of like abuse, or they pull the crimps out. Like I had a kid at Maker Faire that pulled the crimps out, and it's because he grabbed 2 neurons and like just was ripping them as hard as he could, and just like boom, breaking cables. And I was like, no,
that is a tough audience right there.
No,
right?
It was great. That's like the only time we've actually had that kind of failure. But the insidious like bad connection, like wiggle it a certain way and the light flashes, or you get a high resistance. Like I can't accommodate that. And I was a sales guy for a couple years, so maybe I have like an unnatural respect for sales engineers that maybe isn't common. But I was having a conversation with the value-added reseller, my sales engineer from them. He stopped by the other day, and he was just like, "Look, I've had customers that like bought the real JST header, and then they got knockoff JST pins, and like they had intermittent field failures 5 years later."
Yeah.
And like,
oh no, yeah, I get the quality argument. I'm just saying that like that's just, I mean, that's as long as you're measuring that stuff, right? As long as you know that the quality is important to you, then it's like, yeah, of course you're going to pay for it, right? And then maybe you just charge more for it, and it's like. But then you also work that in your marketing where it's like
genuine JST connectors.
No, not like that.
I will totally say that though. I don't know.
Yeah, but nobody knows what that means. I mean, like it's not like there's a neuroscience high school teacher somewhere.
Well, I don't know. Maybe they could.
Maybe it's a thing now.
But so to your point though, I should test it. About a month ago I eBayed a 5.5 digit 4-wire multimeter and a set of Kelvin probes and a GPIB connector, which is like or the old HP like 36
the HPIB, the IEEE 488.
Yeah. So I bought the ProLogix adapter, and I got it to work from the command line, so I can just like I set it up with a test jig, and I put on like some Netflix thing, and I just sat there mindlessly like plugging and unplugging it for 3 hours or 2 hours, and I was able to test a connector to 2,500 cycles, actually like data, like see how it aged, and it was really interesting. I only did it once. I need to try it a couple more times with the same thing, and I want to try it with their gold.
Wait,
flash.
You did 2,500 insertions?
Yeah. Yep. Yes.
Good Lord, man, that's a lot of plugging and unplugging. Yeah. How's your fingers afterwards?
Whatever, you gotta do what you gotta do.
Right. I get some serious connector callus.
Yeah, I got connector fatigue. I need the rest of the day off. On that note, I actually just hired an intern though. So, Jared, if you're listening to this, you're going to be on connector testing duty probably starting next week.
Oh
so
man,
get ready for that.
That sucks. Yeah. That's nice. You're getting.
In all seriousness, I found this guy because we sold these kits to the University of Minnesota, and they were using them in their neuroscience capstone lab course. So they had like neuroscience students were like, as seniors, they needed to build some neuron circuit that they had learned about in their undergrad, and then like defend it to their teachers and use neurobytes for that, which was kind of cool. And then this guy emails me, and he's like, "Hey, my girlfriend's a neuroscience major. I'm an electrical engineering and physics major, and I checked out your website, and I got to play around with her kit when she brought it home, and it was super cool, and I want to be your intern." And I was like, "Sounds good, man.
Sold.
Stop by."
Yeah.
Which was great. It's like I had no idea how to hire someone, and now he's my intern. So it's awesome.
I was just gonna say, if someone emails Zach, he's 2 for 2 on people emailing him, and then them changing the course of his life in terms of personnel.
It's pretty awesome.
Right. Zach, I have a bridge to sell you. RE.
My wife is an architect, so that means she knows a structural engineer that
she'll check on it. Huh? Oh, that's good. Yeah. Oh man, that's good though. Okay, so I guess one last question about this stuff, because we have one or two other things on the list.
Yeah.
But like, who was using this stuff? I mean, so you mentioned colleges, but are high schools doing it? I mean, where do you see it going in the future?
Yeah, high schools and colleges. We've kind of gotten in terms of the number of kids we have out in the field, we kind of have a 50-50 split between the two of them. The challenge is finding high schools that actually are teaching any neuroscience. But we've actually, like when I was in high school, I took biology when I was in 9th grade, and I learned about graphs and and photosynthesis probably. But like now,
well, you know what else you learned, because everybody learned it.
Oh, right.
The mitochondria is the
what are they? I don't know, Chris.
The mitochondria is the someone's shouting at their podcast player right now. It's the powerhouse of the cell.
Right.
It's the powerhouse of the cell.
I knew there was some specific term you wanted me to use.
That's always quoted on Reddit too, so I always see that.
The powerhouse of the cell. Interesting. It's a good one. So anyways, now we go into high schools, and one of them has an anatomy and physiology class. Like that's what they learn about. And anatomy and physiology, you'll have a month of neuroscience. Same with AP Bio and AP Psych. I mean, classes like that, they're starting to have 1 week or maybe 2 weeks of neuroscience content, which is getting to the point where they can justify buying a set of kits for their classroom. It's kind of
right. So maybe it's not like all kits for all kids, but it's
the way we're talking about it is like, well, we're putting together a kit that's going to be around $150, and it's good for 2 to 3 students working in a group, and we can provide up to 2 weeks of curriculum, classroom curriculum for that. And you're going to need to buy 10 kits for your classroom. So it's $1,500 investment, which is, depending on the school, often something that they're able to pay for without having to go to the district level, which is, I don't know. When you're dealing in what we're learning is when you're in education, like you really have to think about like your distribution chain and
Yeah, I was going to ask about that too, because it seems like, so like people, I guess MakerBot was famously trying to sell into a lot of schools, and I think they did succeed, but I think they had a huge sales force for that kind of thing, and doesn't sound like something you'd want to be doing again.
Yeah, I mean, our plan at this point in the short term is direct sales through our website and getting word of mouth publicity at like the National Science Teachers Association conference and at maker fairs, and there's groups like that. And then eventually, we need to get involved with a classroom product distributor. I mean, there's guys that people that their company goes to the schools and sells these solutions. And we're trying to.
Do they all have curriculum attached to it too?
Yeah, typically. So that's part of what we're doing. That's really more Joe's side of what we're doing. Our Phase 2 grant is doing a lot of curriculum development. So worksheets and like general lesson plans and pictures and videos and.
No, that's great though. I mean, like that's the thing I didn't realize. I had talked to a chip company who actually does some university stuff. And they just like hand professors entire labs. And I'm like, oh, I always thought they did it themselves. I don't know why I thought that. Like
not most of them.
All of them? Yeah. I mean, like it makes sense, right? I mean, like that, and it seems like a good idea. I mean, obviously the chip company has a vested interest in doing so because then they get their chips in front of a lot of smart kids and, like it's definitely a sales technique, but I don't know why I never thought that would be a thing.
I'll tell you, I'll give you some perspective on what makes, like, coming from the electronics hobbyist world, what I thought was an interesting representation of how that supply chain is different than I'm used to. One of the classrooms I went into had 20 Arduino kits. And they were all genuine Arduino. They were all full-price Arduino Unos. And they came in parallax boxes, like from the Parallax company. Okay. And I don't know, I thought that was interesting because I always associated Parallax with like the propeller and the basic stamp and all that stuff. And like maybe they've come to an agreement recently.
Oh, well, I'm sure they're a distributor though too. I mean, like that's pretty common where people will distribute other stuff.
Yeah, no, that's
and
true.
And then they can sell full solutions. I was thinking you were going to say, and then I found out each kit costs $200 or something. That's what I expect. Honestly, that's what I expect in education is that they kind of take them by the horns because there is more money to play with sometimes, not always, of course. There's a lot of funding problems in the US, but like just that there are, it's kind of if you are capable of selling into a system like that, then you also once you are in, then you charge more.
No, that's certainly true.
Huh. Well, that's so like what does a kit look like for you? Your stuff. I mean, like
right now, so we're putting together a kit that has like 6 neurons and a power supply, and a couple switches and a bunch of cables and like a little carrying box. And you can do a decent number of experiments with that. A lot of the work we're going to be doing in the next year is going to be building out our ecosystem. So like we built prototypes of like light sensor modules that allow you to build. They're like little photoreceptors. Then you can build a model of an eye that then has like the layers of, cell neurons, in the retina, and sound sensors and other output devices. So like an little audio output, like beepers, so you can like hear every time a certain part of a network fires. And we just want to kind of create more basic building blocks that students can use, so it's less like, well, here's the 5 things you can do with this kit.
Right, plug this together, do this, and this, and then you're done.
Exactly.
You've done everything but neurons ever again.
Like we're close, but we're not to the critical point where like this is fun to play with on its own. And like that is completely where we have to be. Like we need to have a product where like someone does the 5 lessons and they're like, oh my god, we can plug this together and grab all these other sound modules and like build a little neuron synthesizer, or it'd be really easy to build like a little sequencer, for example, or
right. I mean, it sounds kind of like I don't know if you dislike or like the analogy, but it's kind of like what Little Bits does too, right? I mean, Little Bits
absolutely. They're a company that we've learned a lot from and are certainly someone we look at emulating in some cases. Their fundamental concept of like a ground and a power rail that's shared is one that we take. Their purely analog design is not one we take. I mean, the concept of neurons is that they're like kind of internally analog but externally digital and rate controlled, whereas Little Bits is like 0 to 5 volts, and their magnetic connectors, while amazing and novel, are also just not at all suited for what we're doing because we need to have such a higher density of interconnections.
Right.
But yeah, I mean, like a lot of the stuff they've done in terms of like their kit packaging and like
their design stuff is very nice. Yeah,
it's amazing.
I mean, a lot of their stuff is great. It's just that it seems like their scale is a lot higher too in terms of the. I mean, they raised how much money did they raised?
$60 million was the last round.
I don't know what the hell the investors are thinking with that, but then again, I don't know. Like maybe they will be like the educational piece. I understand, but
yeah, there's some big there's some big companies that have bought large kits. I know that. They had a pop-up shop in Manhattan I visited actually, which is pretty cool.
Oh yeah, and they're at the New York, I think MoMA. I think.
Yeah, yeah.
And we probably went to that museum with the same person who we know.
True. Yeah.
Yes.
But what's really interesting about Little Bits is that they still have a commitment to like this open source idea. So they still release all their schematics, and you can still like. What I really like is that you can still buy the connectors, and I hope they keep doing that because I've been buying like their magnetic connectors and building little Neurobytes interface boards.
Oh, that's
so like
cool.
when we built our model of the eye and we needed a light sensor that was like easy to adjust the scale and the span of and like operated on 5 volts and gave me a voltage output. It's like, well, Little Bits already has those boards, so I'm just going to grab a bunch of those.
Yeah.
And that works pretty well. I don't know
cool.
if it's something we'll do forever, but I don't know.
I remember they were trying to do that where they like had like people recommend boards for a while too, and that I think they stopped doing that, unfortunately.
Yeah, I actually talked to one of their when I was at Maker Faire, one of their R&D engineers, like it was at New York Maker Faire, so they're based in New York, and he happened to be there, and like he was checking out the model of the eye, and was like, oh yeah, no, I hope that Little Bits is okay with us doing this, kind of joking around. He's like, we're fine with it. I'm like, damn, that's cool. And we talked a lot about kind of the challenges that they faced in maintaining that program essentially. And it was like,
I can only imagine.
Yeah, I mean, it sounds good on paper, but it's like, well, how much support can you really give this, like, in terms of engineering? Like, once you actually have this idea, it's like, well, now to get it from this idea and this prototype into production is like actually many, many, many engineering hours, and like now we have to look at whether or not the market will support that.
We often talk about that on the show. Of ideas aren't really worth much, so they're nice, but it's the other stuff is the hard part.
Yeah, totally.
So speaking of new ideas, you have new hardware actually, and you've been playing with. And I wanted to talk a little bit about it because you had mentioned kind of some of the struggles with it.
Yes, I only had one. I don't like doing Christmas lists, but the only thing out of my Christmas list this year was a lepton sensor, the 60 by 80 FLIR SPI thermal imaging sensor. So I got one of those, which is awesome, but I haven't really played with it at all. But it seems like a pretty straightforward device. I know Mike Harrison has done he did a lot of the early documentation on that. He actually like pulled a lepton out of a commercial module before FLIR made them available for sale, and released the datasheet. Now you can buy the modules one single piece on DigiKey and download the 50-page datasheet that like tells you the entire protocol and all that. So it's not really a reverse engineering thing anymore, but
I mean, some like creatures though, don't they react to like light on certain? I mean, I guess you already have a light sensor type thing, but would it be possible? Would you need a lot of processing to take like a sensor like that and then have a neuron react to that? Kind of stuff?
So I think what I'd probably do instead is I would get essentially like a single pixel microbolometer, a single long wave infrared sensor, as opposed to a 60 by 80 pixel array. Just because it would be scaled more appropriately, kind of to what our network does, or we would use that what's that Sharp? I think Sharp makes a microbolometer that's like 4 by 16 pixels. There's a couple projects.
Yeah, there are a couple out there now because I keep seeing these thermal cameras that pop up.
Yeah, exactly. So this one is it's a little bit. I mean, the 60 by 80 is small by camera standards, but for a thermal imager, that's like massive.
Yeah.
But yeah, that's more just for playing around with. Then my squadron of ESP32s finally arrived, so I ordered a handful of the ESP32S boards from Seed Studio back in September, and they finally arrived in much after that. And they're just the basic board that's like just the module, and you can solder the module down onto their breakout that just has like a reset and a IO0 button. But it's a neat little board. Like I was able to, I used like an FTDI, one of the TTL serial adapters. I was able to program it and upload some sample code on it. So I made it into a little access point that like served up had a little Mongoose server on it, and like served up a little website and spat like all the open local SSIDs onto a serial terminal and stuff. And I haven't done much beyond that, but it's a really neat little device. And the documentation
is it has Bluetooth on it though, right?
It does, and it's like I don't think the Bluetooth is really documented at this point. Okay. It's like, and the sample programs I was running and then modifying very slightly that I found on like ESP32.com and ESP32.net, like the official forum, and then the site that has like the listing of all the people that have done projects with it so far, basically. Like I checked out a bunch of those, and like a lot of the documentation was like a couple days old when I was uploading it, so it's very much a new thing. But yeah, ultimately, it's a pair of 240 megahertz 32-bit processors that run free RTOS, and then a Bluetooth classic, Bluetooth low energy, and Wi-Fi. And the Wi-Fi can do like access point mode, and it can do scanning, and all this other stuff, all on this little tiny chip that's really cheap.
I don't really understand where that's going. I've been talking about the 32 a lot. The 8266 a lot, just because the low cost of that kind of thing, and the fact that people are like on like you mentioned on Hackaday.io or other places, like hacking on these things and just using them for weird little projects, and there's something there. Like we cringe when we say IoT, but like when you want to talk about like actual things out in the world changing stuff, I think projects like that. Like that's what's really going to do it. I personally think.
Yeah, so. I think I don't know. I think probably in potentially the minority of your listeners, and certainly the minority of like electronics hobbyists, but like the whole IoT thing is, I don't know. Chris, this is like really going to be super nerdy. Did you ever watch Battlestar Galactica, the show?
I never did, actually. No,
so the captain.
I know a lot of people that like it, though.
Yeah, so the captain of the show, Lee Adama, I think it was the captain of the Battlestar Galactica. Battlestar is a class of ship, and the Galactica is the one that he commands. And the Galactica is the only one that survives like this massive apocalypse at the very beginning of the series, and it does so because Captain Adama like refused to network the ship. He's like, I don't want the ship like becoming sentient and like being able to communicate every little thing that's going on in every little bit of the ship continuously. Like I need to have like the dead the dead man switch or whatever. There's more to it than that, but just the idea of like sensors becoming more and more ubiquitous in our lives. I think it's something to be careful with.
Right. Well, I was going to ask if you're, if so you think that the neurotinker is going to end up training the young scientist that ends up creating AI or implanting electronics into into a neural net or a human neural system or something.
Well, I don't know. So we're one of the operating modes we're going to put in the next iteration, and this is one of the reasons we want to go to the 30
the kill all humans mode. Is that what it is?
Exactly. Yeah, totally. Yeah. No, is a LTP mode for long-term potentiation, which is basically the process in which a neural network changes relative weightings of inputs in response to stimuli. So essentially learning. So right now our networks are static. And because of that, you show it's like an artificial neural networks person, and they're just like, oh, like you flash LEDs. I'm like, well, no, we teach people about biology, and it's like we have different goals. But once we actually can build the flexibility into the system to change weightings and actually change based on stimuli, we can actually start building really, really simple circuits that learn. Having said that, like neurobytes will never be able to match what artificial neural network guys were doing 25 years ago, because like right now they're dealing with 50 million node networks, and that would require 50 million neurobytes at 20 to 30 amps a piece.
Just the connectors alone would sink you.
Just the connectors and power plant that you need is going to be a problem.
And how are they doing that? Are they doing that on chip somewhere? Is it just simulation?
From what I understand, it's done. People have done it in FPGAs and in ASICs and so forth, but I believe most of it is just done on normal PCs and like using GPU processors and stuff like that. And I guarantee you there's a lot of people listening to your podcast that like know a lot about that, and I hope that they bring it up, because you should get some artificial neural networking guys on here, and
I would love to talk to them. I have no idea about any of that stuff. So that's a great application.
Every maker faire I go to, I have one or two of those people that show up, and they just blow my mind, and it's really fascinating. But yeah, to that point, I think our core mission is to like get 13 and 14-year-olds to start thinking in terms of like membrane potential and thresholds and weightings changing, and like so if you can have someone that starts to intuitively understand how a network can learn, That's the hard part. It's a little easier for them to scale that up to a massive network once they understand the basics. But I think what we're trying to do is really blunt the leading edge of the learning curve in terms of neuroscience and so forth. So we could be partially responsible for the AI singularity and all of those horrible things. Thanks, Chris.
They'll call it Battlestar Gazakita.
Yes. Nice. You must have written that down ahead of time.
No, I did not. That was terrible. I'm sorry.
So that's me. Those are my new parts. I want to hear about the new parts that you have that you're going to be building stuff with. Do you have any?
No, nothing super new. What did I get? So okay, so this is actually learning related because so you're talking about teaching high school kids, and sometimes when I'm writing code, I feel like I'm an elementary school kid, but I was going nuts over. So I mentioned on the show we had Tony from Adafruit on, and he was talking about MicroPython stuff like that.
Yeah, I heard that episode. Yeah.
Yeah, and I was just going nuts because I was trying to program these sensors, and I just couldn't get it to work. And so sometimes I think the thing is with like kits, the important thing about kits is the fact that they're all the same. And so what I did is like Tony had a bunch of tutorials, and I was trying other sensors and just trying to figure out what would be different, and just because I had them on hand. And I thought I was going crazy, but then I tried this. They were like SparkFun sensors, so I tried the SparkFun sensors with the Arduino board. That worked fine. And then I tried them again with the MicroPython thing. That wasn't working, so I'm like, you know what, screw this. And I went back and I just bought all the stuff from Adafruit that I, like the sensors to have the exact example. That is such a key part in learning when you're starting out of like, I just want the muscle memory at the beginning, like the learning path you're talking about. Like I just need to get to the end of it. So I just got some new sensors and stuff.
That's awesome. That point that you made, I completely agree with though too. I mean, I was playing around with the STM32 F0. I had like some of their discovery boards. Yeah, and I wanted to get ST-Link and the command line tools working on it, and I wanted to use libopencm3 and all this other stuff, and like. The only way I was eventually able to get it to work is by exactly duplicating everything that someone else had done, which is so because that's what happens when you're dealing with like layers of abstraction, and you're like, oh well, I have the LM3974DF instead of the DC, and it's like, oh, the
you're
DF
just looking for whatever's different, right?
Yeah, like the DF uses like a different speed I2C bus, or like it's got a different address, or it's got something else that like is dealt with in your abstraction layer way off to the side, like you don't ever want to have to touch, and it just doesn't work.
You didn't know that, Zach.
Yeah, come on, man, read the manual. No, but and on the manual thing, back to the ESP32, there's kind of this double-edged sword where they're like providing this really low-cost device, and they're crowdsourcing a lot of the documentation. But then
it turns out the cost is in the paper, huh?
Yeah, well, but I think about what I do at NeuroTinker, and I'm like, I would never use a part that didn't have a data sheet that I could like rely on.
It's almost a liability.
And not to say they don't do that, and they like that's probably not a great example, but I think just in general, there's this balance where like you're tinkering around with stuff and getting it to work quickly, but if you actually want to scale it up, like you need to understand the supply chain. You need to understand like the device specifics that are in the data sheet.
That is a huge piece, right? That'll bite you every time. It's like, oh yeah, no, you're buying the wrong. Yeah, that's not good down to minus 40 C or something like that.
Yeah.
Oh, I guess I should have checked that. Yeah.
We do have to worry about that in Minnesota.
That's true, you guys do. Yeah. Not much warmer here, to be honest.
Yeah, that's true. So what sensors did you get with the Adafruit?
So I got a couple sensors. My box is in my book bag. But it's just a simple temperature sensor, like an I2C temperature sensor. Like I think it's a MCP, maybe not. I don't know. That's the other thing where it's like you're treating like sensors now, where I'm just looking at as on this specific thing as just like code.
Yeah.
It's like, oh, but eventually I'd have to dig down into it. And then I got one of the screens as well, because I've never done any display stuff, even with like simple displays.
Oh, okay.
So I got some of their display stuff, and I'll be trying that out.
Yeah.
My goal, I think I've said on maybe last week's show or the week before, but my goal in 2017 is for the show is, like I mentioned, to get more people on application wise, but for me is to do more prototyping in general. Just like, and I think you do a lot of prototyping with your soldering method, right? You do a lot of cut and solder type stuff.
Yeah.
But
I found
I always get really caught up in like, oh, it needs to be a board, blah blah blah.
Yeah.
And I think you're doing it right, to be honest.
Yeah. So I had this. I'll give you an example. I don't want to like waste your entire evening or whatever, but I had an example where I constrained myself when I was prototyping. I think it's really important to do that. So I have we have a cabin in northern Minnesota that has like no cell phone coverage and no internet access and all that stuff. So I lugged my oscilloscope, my soldering station, and like all of my parts and all this other stuff up to the cabin. And the objective was to build a oscilloscope for the neurobytes where you could like visualize the membrane potential essentially. So it's like you could plug this thing into a neurobytes board and it would graph in the time domain, the real time membrane potential value, and you could actually see the spikes and all this other stuff. And the only
so you missed out on something that you said you brought with you. What did you bring with you on like manuals and stuff?
So
or data sheets?
So before I left, I was very careful about what I brought. I brought and this will be like a big plug to the work that Paul Stoffgren has done. I brought my Teensy 3.2. And I brought one of his 240 by 320 TFT LCDs. And I brought the entire book that he printed out and passed out at the Hackaday Super Conference in 2015 when he did his audio workshop.
His workshop.
Yes, because it was like written documentation that was like, this is an SPI display, and like these are the pins that you need to use, and then this is the library that you download, and this is how you get pixels to do this, this, and this. And it was just like, once you have. I basically was able to like know when I left Minneapolis, like I have all the documentation I need. Like I have 2 PDFs and I have this binder, and like I know I should be able to mash those together and be able to like master this display. And then I brought
make a thing.
Yeah. And then I like so I knew I could figure it out on the code side, and then I brought up like a couple pieces of FR4 and a razor blade and some flux and like a bunch of solder and like, well, I don't know, the cut, the carve FR4 and apply flux and then like solder it and kind of Manhattan style ish, I think really lends itself nicely to getting breakout boards to behave. So if you have a bunch of modules and you want them all to be in the same place, you can just, rather than soldering on straight headers, you can solder on 90-degree headers so they have like a flat side and they just kind of surface mount to a piece of FR4 and just point to point wire it from there and put in resistors and stuff. And it ends up being suitably compact and durable, and something that you can make that day.
I think followers of the subreddit or the Twitter account may recall I've tweeted at least 2 of your masterpieces. One that I saw, I think, was part of the scope thingy.
Yep. Yeah.
Or it was at the same time that I saw it.
That's probably right.
And the other was that when you took a QFN and you were soldering enameled wire to it.
Yeah. When
I still don't remember why you said you were doing that. You just yelled at me for posting it to Reddit on your behalf.
Yeah, because Chris, I didn't get any karma for that.
Sweet
we've
karma.
both been on Reddit for a while, man. I checked out your account. You're what, 8 years? I mean, it's almost as long as me. I have 9 years. No big deal. Like I'm not counting, but I did check it before we got on.
How many points? How many fake karma points?
Okay, less than you, so I could have used that, but not a big deal.
Post to the subreddit.
You're
Posting up our subreddit. Yeah. You will surely get that.
I will do that. Do that. But no. To answer your question, I had bought a couple of Texas Instruments 16 channel constant current LED drivers just to play around with them, and I just bought the ones that came in 24-pin QFN packages. So it's like, well, if I want to use this on a breadboard, I gotta dipify it. I don't know. Excellent. I got into this hobby because I'm obsessed with soldering. Like that's where I have to remember, like that's where the passion for me comes, is like getting the soldering iron out and physically melting metal and making stuff stick together. Like that's it, man. Like flashing LEDs are great.
Where did
too.
that come from? I don't like. Did you?
Yeah. So when I was like 7, my great uncle, who was an electrical engineer, he gave me a VHS tape, and it was the Heathkit Guide to Soldering.
Oh my god! Yeah. Do you still have it?
I don't. My mom might have it at home. I gotta check when I'm back in Columbus. I'll take a look, because it's amazing. Like it gives you all the good practices, and like clean everything and use flux, and like this is what rosin core flux solder is, and like don't use the acid core flux that your parents have for sweating pipes, and like and what was really interesting is like we're using 60-40 solder. It's like, well, tin melts at like 400 something Fahrenheit and lead melts at 600 something Fahrenheit, and like solder melts at 270, and like why is that? And then they show a picture of a binary phase diagram, and like I don't know. I told you this like before we started, but like that's why I became a metallurgist. Is because like I remember seeing a phase diagram when I was a kid and like learning why my soldering iron could melt a tin lead alloy, but it couldn't melt tin, and it couldn't melt, or it could, but it would take longer. So it's an amazing video. But of course, it doesn't talk about surface mount stuff though.
I'm trying to see if I can find it on YouTube right now. Yeah. It was called the Heathkit Guide to Soldering. Is that right?
Heathkit Learn to Solder or something like that. I want to say it's like 45 minutes or an hour long or something like that.
Oh, dude, you got to digitize that. I mean, like,
I'm gonna
Heathkit, I know people are going to say, oh, they're coming back. Whatever. They're not coming back.
Yeah, they're, oh, man. So, I appreciate the aesthetics of those kits they released, but, like, no, it's not the same.
That's a different era, right? And it's fine.
Okay,
but
so the other Heathkit thing that I have that was really cool is they had a bunch of recorded, like they had these big binders that like had all these project plans and stuff, but they also had these like really thin records. They were like the thickness of a transparency sheet, but it was like a 45-minute, record. And they were just really fun.
Wait, were they the ones that you like? Oh, the paper records?
Yeah,
were they paper?
It was like plastic. It was like blue plastic or like red plastic, and they were like as thin as a transparency sheet.
No. I just remember like McDonald's. I remember when I was like really young, McDonald's gave away a record that you could play, but it was like a toy record, basically.
Awesome! Wow. I'd want to be involved in like the engineering of that like that supply chain, like figuring out how you can stamp paper records for like essentially the cost of stamping paper without a record.
Yeah. It was even just seeing how actual records are made there's some great science there too, but like just like the wax press and stuff like that.
Have you seen Ben Krasnow's when he did the video, like the GIF of his SEM watching the head, like that's what head of a record? Like it was so cool. Like he ended up just like having to take a whole bunch of images and then like stitch them together on his SEM. But very neat to see that.
No, that's what it was. Is my so we did like a unconference day that I think I mentioned on the show in the past, but I think I mentioned that last week. But one of my other coworkers went over how records were made, and then she referenced Ben's video and showed us that other video on how records are pressed.
That's awesome.
So, yeah, it was really cool.
I'm glad people are like still interested in documenting that technology, because I think at some point someday like the need to really precisely measure like 90-degree out of phase tiny bumps using a stylus, I'll bet it'll be relevant to someone in like 30 years, and they'll be like, oh my god, this already exists. I just need to find a record head from like 100 years ago.
Find me a hipster.
Hey, in Minneapolis we have those.
Oh yeah, up there too, huh?
Yeah.
They're everywhere, man.
Yeah, it's all right.
Okay, so still, are you doing? I feel like there should be like a soldering challenge. You know what I mean? Like,
yeah. So there was one, and it was posted on Hackaday. I think like 6 months ago. Someone made a board that like basically was like a 555 LED flasher, and you just made it like 5 times. You made it with dip. You made it with like SOIC. You made it with whatever the smaller SOIC that's wider. And you made it. I don't know if you made it with the QFN or not. And then the LEDs, you go like from T1 3/4 insertion LED. Then you have like an 0805 and an 0603 and an 0402.
Oh, cool.
And then they like the idea, and then they have like a resistor and a capacitor for each one. The idea is like you solder this together as fast as you can, and if they all blink, then your time is out or whatever. And I've been
kind of like that scene in Social Network where they're drinking tequila and they have to like break into a server. So like we should do that, except it should be bourbon, and we should use really hot soldering irons.
Yep. No, I agree with that. And so I'll see if I can find that. I'll see if I can see the link to that too.
I've planned for a while. I haven't done it yet, but I do have plans to make an obstacle course. But it was more about bodges than it was about fast soldering.
See, I think we should do a collaboration on that or talk about it more, because I really think that would be fun. And you do it standardized, and you like have the whole thing out there so anybody can spin the boards up, and you have standardized components, and it's like anybody can like get their own time on this and see where they stand. And we need to
I was just honestly just going to do it like you just need like a reel of 0 ohm resistors, because then what you do is you put a final resistor in line, and then if the LED lights up, then like it's all tied together.
That's a really good point. Yeah.
And then the idea though is like, you have to TP 2 resistors, then you have to I always call it Stonehenging. I don't know if other people call it that.
Yeah, then, the graveyard, the graveyard of tombstones, man.
That's right. And then
I see. When you put one up and you put another one up and you put a third one to bridge it.
Right. You need to put 3 resistors in line on a single resistors pad, right? If you want to make 3 resistors in series, And then another one would be like, you need a double stack. That's easy, whatever.
Oh yeah. Did you see the guy on Reddit that did like a 20 stack? I think it was on the PCB Reddit maybe.
I did see that one. Yep.
Yeah, it was ridiculous.
He's like, when you really need a lot of power in a resistor or something like that.
Yeah, it's like you need new traces, man. You breathe on it and it flips over, but.
Well, and then today I was tweeting with Micah Scanlime on Twitter, and she had posted a bodge to like flying wires, and I had proposed that be called an alien landing or something like that. But I was thinking like sometimes you need to do that too, where you're going from like, if you need to go from a resistor to like a via, right? You need to like solder to a via. That's happened a lot for me where you need to just access some other point, or you need to cut a trace, you need to scrape a trace. That's so
yeah, I think something bodging related would be a good one. I don't know. I see it posted a lot where it's like, oh, it's like the ugly style or the ugly way. It's like, no, I think it's neat. I really like it. Yeah. And I've gotten really into this clear polyurethane wire. I get this. It's like 34 gauge. I bought a spool on Amazon. It's like 2,000 feet of this stuff, and it's polyurethane insulated. So you just like touch it with the tinned iron and like dip it in. So
it's kind of like the magnetic enameled wire.
Yeah, it's enameled It's essentially magnetic enameled magnet wire. Yeah, that's exactly what it is.
34 gauge. That's
34
that's
gauge.
impressive.
Yeah, which is about. It seems about right because that's like small enough that you can basically tack it on. Stuff that's
like 0.5
or 0.65 millimeter.
Yeah.
You just kind of do it in the right order.
Do you use magnification or no?
I have like a 3x ring magnifier that I use. Huh? Yeah. You know what else? You know what else I use?
I don't know.
I use lead-free solder exclusively.
Whoa.
Yeah.
Them's fighting words. Well,
I know,
you know what? Actually,
I know. So I'm throwing down the gauntlet. Anything that you can do with lead solder, I can do with lead-free solder.
I'm squarely in the lead-free world now myself because my lab is in my kitchen.
Yeah, well, and I make kids products. I make stuff that like middle schoolers are going to handle at like a maker fair. You can't mess with that
idea. Start them with that though.
Well, yeah, I don't know. It's not that hard. It's not that different. Like, I don't know. I don't think the kid's gonna like build a nuclear submarine that needs to be worried about pin whiskers and like. So the two issues with lead-free solder is like it's got to operate at a higher temperature, so like oxidation and all the temperature related shit is a little bit harder, and the solidus to liquidus distance is a little bit longer. So like 60-40 solder is like very close to the eutectic. So like when it solidifies almost instantly. But like lead-free solder, from my understanding, you have to be more careful when it's solidifying that you don't move it around or you'll get cold joints. But like, I don't know. I think it's just you just get used to it and then it's not an issue anymore.
Yeah, no, I think that's the way I think about it is you don't tell a kid that beer's awesome, right? You let them realize it's awesome when they turn 21 or around thereabouts, right?
Yeah.
And that's what they'll figure out with leaded solder too. They'll be like, oh,
yeah,
this is great.
And I didn't need this in my youth. I look at it from it's a more somber perspective, I guess. But like, if we want to bring more people into the hobby, the way to not do that is to have
poison them
stuff. Well, like so the real danger with soldering is like the flux vapor. Like the lead's never gonna hurt you unless you like eat a spool of solder. Like that's been established. But like at this point, like we've lost the marketing contest against lead. Like.
Oh right.
You can't like you just can't have lead in stuff anymore, and like whether or not it's superior in every way, like it's kind of irrelevant if you actually want to get mom to like let little Johnny solder stuff.
That's a good point. Yeah,
that's
especially for educational stuff. And, but just in general, I think that's a really good point.
Yeah. Bring on the hate. But I'll tell you what,
I'm not gonna say it's not awesome, but it is awesome. But I think that you make a very solid point there.
Yeah.
So.
Well, honestly, the biggest disappointment is like leaded solder always just makes a nice looking joint. Like it's not even like that. It's necessarily a better joint. It's just always shinier. It's like way shinier. That's true. And it's
right. It's not dull.
Yeah, it's frustrating, but you get used to that.
Well, Zach, we are now an hour and a half plus in. Is there anything we missed?
Oh man, I don't really think so. Thank you for getting in touch with me, man. It's been an honor, and I've really appreciated the time. It's been fun to talk to you about this stuff.
I'm glad that we've
really been
dovetailed
awesome.
on similar interest here.
Yeah, absolutely. So. And I will come out to Chicago sometime too. Actually, yeah, that'll happen soon.
Excellent.
we'll have like
you might want to wait until summer, but you know,
yeah, that's fair. You should come out.
You're used to the winter.
Come out to Minneapolis. You should come up to my cabin this summer. Boom. Do it.
So we did actually talk about the whole idea of an isolated design contest at some point. So maybe we'll have to play on that idea some more. I think that's very impressive, by the way. And
it's a really fun way to constrain yourself. It can be. I mean, it can also like. It could have been horrifyingly frustrating if I had left my flux at home or something.
And then I made flux out of tree sap.
Yeah, totally. Ish. Yeah, or like had to use plumbing solder or something like that. But yeah.
No, I just mean like the isolation piece too of like I'm so addicted to like just Googling data sheets or Googling solutions. Like it really does change how you figure stuff out. And I think that like I saw former guest Todd Bailey, I follow him on Twitter, and he was talking about like he isolated himself over the winter break and read the USB standard.
Wow.
Which seems like the only way that you could probably read that.
It's like 1,000 pages or something, isn't it?
Yeah, dude.
That's crazy.
I'm guessing there's beer.
But that's awesome.
Beer
I mean, that's great.
But yeah.
Well, I mean, if you can make it to northern Minnesota in the summer, certainly not winterized, I would be happy to. But I would be happy to host an isolated electronics design party. That would be fantastic.
That'd be cool. All right. Well, thanks, man. And people, where should people find NeuroTinker?
Neurotinker.com. My partner Joe runs our Twitter account, so that's @NeuroTinker.
It's NEU, right?
NEURO. NEURO. Do I have NEUROTINKER. I had to check my sticker of that on my phone. And then I run our Instagram account, which is also @NeuroTinker. And then if you want to read like kind of an exhaustive history of the project, search for Neurobytes on hackaday.io, because that's where all of the documentation for the last 2.5 years has lived and will likely continue to live.
Right. And I'll link all those in as well.
Yeah. So cool. Thanks a lot, man. This has been a lot of fun.
Awesome. Thanks, Zach. We'll talk to you soon.
Yeah, sounds good.